So we started with limits, which included continuity, discontinuities, one-sided limits, using limits or evaluating limits with a graph, algebraically. Then we moved into derivatives. So we learned what a derivative is. So just as a review, what is a derivative?
A derivative.
Just in general.
The slope of a tangent line.
Slope of the tangent line. Okay. So we had all of those. So we learned what it was and what a tangent line was. And then we moved into all those derivative rules. So we had the power rule, which was nice because it shortcutted a lot of stuff. And then we moved on to the product rule and the quotient rule. And then we hit the chain rule. And then there was implicit differentiation. I think we ended with related rates. And then chapter 3 was all the derivative application with a graph. So learning what happens when if the derivative is positive or negative, what does that tell you about the graph of the function? And then we ended with all the basic stuff with integration. So do you just kind of want to start in the beginning and go through it, or are there certain areas that you guys as a whole would like to focus on?
There's one problem. It was from the beginning of the chapters that I wanted to go over.
Okay, well, I meant like topic wise.
Topic wise, let me find the topic for that. Forgot the exact topic name.
In general, for me, I found this middle 2 chapters the hardest. The chapter 3 and chapter 4.
Oh, okay, so the derivative, all the stuff with derivatives.
Yeah,
Yeah.
I'd like to go over some of the stuff where you had a function and you had to find where the concavity is, where it's increasing and decreasing, those really long problems.
Yeah,
where you had to find all that stuff.
Yeah, that's confusing.
Okay, just bang the table. Sure. Okay, so let's f of x equal, we'll just say, well, I'm just going to do a polynomial. So we'll do x to the 4th minus 5x squared plus 4. And find everything. So where it increases, where it decreases, all the relative extrema, inflection points, the intervals of concavity, and so on and so forth. Okay, so if we're going to find all of that, where do we have to start?
Getting the first derivative.
Getting the first derivative. Okay, so what is the derivative of this?
4x cubed minus 10x.
Okay, so then once you have your derivative, you can set it equal to 0. And then you can solve for it. So if we solve this, what are we actually finding?
The critical numbers?
Mm-hmm. Yeah, the critical numbers. So let's see, we can factor out a 2x. So we have 2x squared minus 5 is equals to 0. So x is going to equal 0 and plus or minus what?
Square root of 5.
That's in it. There's more stuff to it
Root
though.
of 5 halves.
Yeah, square root of 5 halves. All right, so these are your critical numbers. So then once you found them, what did you do with them?
Plug them back into the original function.
And what would that give you?
The relative extrema.
It would give you the y coordinates of the extrema. But we usually didn't start with that. Like, I guess you could. But usually, like, once you found your critical numbers, then you started to use the first derivative test. And how did that go?
Is that the number line?
Yeah.
Yeah, okay.
So yeah, you made your number line. And just so you know, if you have a problem like this on the exam, the numbers would be a little nicer since I'm not making the equation up off the top of my head. So you're not going to get typically going to get a critical number of root 5/2 since you can't use a calculator. Okay, so you set, excuse me, set up your number line with your critical numbers on there. And then what did you do from here?
Plugged in numbers within the bounds. So like -2. Some number between 0 and -5 halves. Or
Yeah,
yeah.
well, -1.
Okay.
1 and 2. Okay, and then so these are your test numbers. And then where did you say to plug them in?
Into the first derivative.
Yeah, into the first derivative. And all you care about is if it comes out as a positive or a negative. So if you take the -2 and stuck it into this one, the factored one, does it come out as a positive or does it come out as a negative?
Negative.
Okay, and then for the -1,
That one's positive.
okay, the positive one,
That one's negative.
and the 2.
That one's positive.
All right. Okay, so you're decreasing are all the intervals that have the minus signs. So at negative infinity to negative √5/2. And from 0 to √5/2. And then it's increasing for all those plus signs. All right. So there's your intervals of increasing and decreasing. Now let's get your relative mins. So by looking at your little sign chart here, how do you know if you have a relative min in that chart?
It switches from negative to positive.
Yeah. So it switches from a negative to positive, that X value, and then at this one. So at the fun numbers of √5/2s. Okay. And so then if we did what was suggested a while ago, we just take those two X values and stick them into the original, and then that will give you your Y coordinates. So if you raise the negative root 5/2 to the 4th power, that'd be 25 fourths. Minus, if you squared it, that'd be 5/2 times the -5, 25 halves. Plus 4. So you can combine the two fractions to -25 fourths plus 4, which would give you a total of negative something over 4.
To confirm, when the sign switches from negative to positive, it's a relative min, right?
Yes.
Be -9/4.
Yeah. And that's going to be the value for both of them, because your exponents are all even here. So it's not going to matter if you plug in a positive or a negative. The 4th power and the square are going to make a positive anyway. Okay, so the relative max, that's going to be the opposite. That's when it switches from a positive to a negative on your sign chart. So that's the nice one, because that's happening at 0. So when X is 0, Y is 4. All right, do you guys have any other questions on this one? Or on what we've done so far before we go into the second derivative step? Okay. So let's hit the second derivative. And go from there. All right, what's your second derivative?
12x squared minus 10.
Yeah. Okay. So you can set that equal to 0. And when you solve for X on this equation, what are you actually finding? Potentially.
Inflection points.
Yeah. Okay, so we got another fun value. So plus or minus the square root of 10/12 or 5/6. So you can set up another sign chart, this time with the second derivative. So you got to choose your test numbers again. So in between them, we can go with 0. What do you want on the ends?
-1 and 1.
Okay. If you're not sure, like, is -1 smaller than this, then just make it a more negative. So you can go like -10 or something. Okay, so when X is -1, plug it into your second derivative and it comes out as
Positive.
positive. You stick in the 0.
Positive as well.
Not quite.
Oh, sorry, for 0. Negative.
Yeah. And if you plug in the 1,
And positive.
positive. Okay, so we've got concave up. And all the plus signs. So negative infinity to negative root 5/6. And then roots 5/6 to infinity. And then concave down at all your minus signs. So just in between the root 5/6s. Okay, so now that you've tested with the sign chart, now you can definitively say where your inflection points are. On the third exam, I can't remember which question it was. I think it was, might have been question 3. It gave you a function and it said it wanted to know where the inflection points were. And what a lot of people do is they find the second derivative, they set it equal to 0, they solve for x, and then they stop. And they say, oh, the inflection points are all these x values. But what they forget to do is they forget to actually test them. So in order to be an inflection point, there has to be a sign change in your second derivative. Just because you solve for x and got an answer doesn't mean it's an inflection point. So it's a little bit more involved than just finding a critical number. Critical number, you just solve for the derivative is 0 or undefined, and then that's it. That's automatically a critical number. Not so much with the inflection point. You have to test those x values to see if there's a sign change in that second derivative. So if there's no change in it, then it's not an inflection point. Okay, so but for here, both of them had a sign change, so they're both an inflection point. We just need to get the y values with them. Okay, so stick these back into your original function. So if we raise that radical to a 4th power, that'd be 25/36. If we square it, that would be 5/6 times a -5. So 25/6 negative, and then plus 4. So if you combine the two fractions together, that'd be -125/36. And then plus 4. And then if you finally added the 4 to it, 36 times 4 is 144. Oops, extra negative in there. And then 144 minus 125 is a positive what?
$19.
Mm-hmm. All right. So there's your increasing, decreasing, extrema, concavity, and your inflection points all in one. So any questions on the second derivative stuff? Okie dokie. Okay, so you guys think you're okay with that, or do you want to try another one with a different type of function, or are you good?
I think I'm okay on this one. So when does I remember the second derivative test fails at some point. Is that when
Yes.
it equals 0? I can't remember.
Yeah,
Okay.
so let's talk about that for just a minute. So second derivative test. First off, what is a test for? Like it's a test for what?
For concavity.
It's actually not. It's easy to think it is because that's what we just used it for. But this is not the actual second derivative test. So the first derivative test and the second derivative test, they actually test for the exact same thing.
To test for max and mins? Or-
Yeah. Mhm.
Okay.
It's a test for your relative extrema. So both of them
Right.
do or accomplish the same goal. And that's all they do. So if it asks you, if it says, is the first derivative test a test for increasing and decreasing? The answer would be no. It's a consequence of the test, but it's not what the test is doing. The first and second derivative test only test for extrema. That's their purpose. Okay. So how did the second derivative test go? Okay, so let's C be a critical number of F. So there were three kind of cases I could come out with this. So if you plugged in that critical number, that C value, if you plugged it into the second derivative and it came out as positive, did you have a relative max or a relative min?
Relative min.
Yeah. Okay, and then if it was the opposite, if it came out as negative, then it's the opposite of relative min or relative max at the x equals C. And then the third case was the one that I think it was Christina mentioned. That's when if you plug in that critical number into the second derivative and it actually comes out as 0, then the test fails. So when we say that the test fails, does that mean there's no extrema there? Like, do you just get to stop and go, oh, no extrema, and then move on, or do you have to do something
No.
else?
You go back to the first derivative.
Yeah. Yeah, so use that first derivative test. I've said it before, when I was in Calc 1, the only time I ever used the second derivative test is pretty much when it told me to. Because I was like, well, if it has a possibility of failing, I'm just going to use the first derivative test anyway. Plus, you have to get your critical numbers. So you're kind of right there to use it. Where it comes into play a lot more and where it's really useful is when you get into calculus 2 and calculus 3, because there's formulas that you'll use in those classes that where the second derivative like comes up. And so you can figure things out a whole lot faster if you remember this test. That's all I can say on it now because you're not in there yet. Okay, let's see. How are you guys at obtaining data from the derivative graph? You want to try one of those, or you guys think you're okay?
If we could go over that, that would be awesome.
Sure. Yeah, we can. Let's go over anything we want. Okay, so let's. We'll just do this. Okay, so that intercept there, that we'll put that at negative 5, or no, -6. It hits the origin, and we'll make this intercept a +6. And then the top of this curve right here, that'll happen at x equals -3. And we'll make that y value 4. And then same thing down here, we'll make that a +3. And down there at -4, so kind of nice and symmetrical. And this will be the graph of f prime. So this is the graph of the derivative. Okay, so we're going to use this graph to answer questions about the graph of the function which you cannot see. So we'll start with this. Where is f increasing? So let's kind of break that down just a little bit. If we know that the function is increasing, what does that tell you about the derivative?
And it's positive.
That is positive. Okay, because if the derivative is positive, that's what we know that the function is increasing. That's what we just did in the other problem with that sign chart. Every plus sign, every interval that had a plus sign on it, that's where the function increased. So we're doing pretty much the same thing. It's just we're translating it into the graph instead of your sign chart. So if we're looking for where the derivative is positive on the graph, that means you're looking for any section that's above the x-axis, because that's where you would have all your derivative values being positive. So on this hill and then this end section here. So that would be from starting at x equals -6 to 0. And then union from +6 to an infinity. And that is where F is going to be increasing. Now notice that these are intervals, they're not points. So I'm not talking about the 0.6 comma 0. I'm talking about the interval of the X values going from -6 all the way over to X equals 0. So this whole section. Okay, so then the flip side of that, where is F decreasing? So if the function is decreasing, that means your derivative has to be negative. Because again, when you look at that sign chart, it's, you know, the function is decreasing everywhere you had a minus sign, which is indicating that the derivative is negative. So that's any section that's below your x-axis. So this first section here, and then this little valley part. So negative infinity to -6. Union from 0 to +6. All right, any questions on these first two? Okay. So all relative extrema, that means you're looking for your relative maxes and your relative mins. So there has to be a sign change in your derivative. It has to switch from positive to negative or negative to positive. But when you translate to a graph, that means it's switching from, you know, below or to above the x-axis or from above to below. So your relative mins, those are going to be where it switches from minus to a plus or from below to above. So that happens at the -6 and then again at the +6. Okay, now notice I did not give y coordinates with those. So why do I not do that? Do you guys understand what I'm asking?
So for the relative minimum, why you only need the X value?
Yeah. Like, why are you not able to find the y value?
Because
Well,
we don't have
a
the original.
function. Yeah.
Yeah, because anytime you want the y coordinate, you always plug the x value back into the original function, but you don't have it. So you can't give a y coordinate. So it's not this point, it's not -6 comma 0, because that's where this point is again, because this is with the derivative, not the function. It might be at -6 0, but you don't know for sure. So you can only give the x values. All right, so then the relative maxes, That's when it switches from positive to negative or from above to below. So there's only one value at x equals 0. Okay, and then part D. Let's do it all at once. Identify intervals of concavity. So let's tackle the concave up first. So if the function is concave up, what does that tell you about the second derivative?
It's positive.
It's positive. Okay, so if we had the graph of the second derivative, we'd be good, but we don't have it. We have the graph of the first derivative. So we need to relate the second derivative to the first. So if your second derivative is positive, what does that tell you about the first derivative? What does the first derivative have to be doing?
Wouldn't it have to be increasing?
It's increasing. So if something's derivative is positive, then that something is increasing. So the derivative of the derivative is the second derivative. So you're basically looking for where this graph itself is going up, or it's increasing from left to right. So that's going to be from negative infinity all the way to -3. And then again, from 3 on up. Okay, so then concave down, now everything's just reversed. So your second derivative has to be negative. So if the second derivative is negative, then the first derivative is decreasing. So that's only happening in one section from there to there. So from -3 to 3. And then I have one more thing I can ask you about the function using this graph. So what else can we find?
Maybe like inflection points.
Yeah, that's the last thing we can get. And again, we can only get the x values with them. We don't know the original function to tell us the y's. All right, so the inflection points are going to occur whenever the concavity switched. So when you're looking at the graph of the derivative, it's where it's switching from increasing to decreasing or vice versa. So it's basically the relative extrema of the derivative. So that would be at your -3 because it switched direction. And then again at the +3 because it switched again. Okay, you guys think you're good with that?
I see. Let's see what in India it's probably made it a bit different compared to in the UK, but they both are value praise. So Indian viewers don't get angry. It's just a different way they make it in the UK.
Okay. Let's see. Do you guys want to try a related rates problem? Do you remember what those were?
Yeah, that would be helpful.
Okay. So that was the application for chapter 3. And then we had another application for chapter 4. And they're kind of similar. But the related rates, those were the problems where it was like, something is moving at a rate of 2 meters per second. How fast is the volume changing when that is 4 units or something like that? The one in chapter 4, that was the optimization. That's when you're looking for like, what's the max area or what's the minimum distance or something like that. Okay, so let's see. A rectangle is bounded by the X and Y axes. And the function y is equal to, let's go 36 minus x squared. So a particle starts at the point 0, 36. And slides down the curve towards the point 6, 0. So the x coordinate is moving at, we'll make it kind of interesting, at 1/2 meters per second. How fast is the area of the rectangle? Changing. This is quite wordy. when X is equal to, let's see, Cameron, give me any number between 1 and 5.
3.
3. Okay. All right, I'll give you a second to either write it down or think about it for a moment. Okay, let's go ahead and just draw it out so you can visualize it. So your function 36 minus x squared, that's just an upside down parabola. But we're just looking at it basically in the first quadrant because it's bounded by the curve, the y-axis, and the x-axis. So there's a rectangle in there. And it hits the curve at the point xy. So the top of the curve, that's your 0.36. And then right when it hits the x-axis, that's your 0.6, 6,0. And so we're ultimately talking about the area of that rectangle and how fast it's changing as this point is basically sliding down. So the rectangle is changing shape as that point moves or slides down. So it's pretty tall but skinny as it's, as it's close to the top, and as it moves, it gets shorter and wider. Okay, so these were the problems like in the notes. These are the ones where it had those, like I guided you through those 3 categories: the know, the given, and the find. You don't have to use that if you don't want to, it's up to you. So I'm just going to do it just as a refresher. So your know category, those again were the formulas and stuff that you've dealt with prior to this class. So area, volume, trig functions, Pythagorean theorem, distance formulas, slope, like everything that's already in your head before you started this class in August. So with this problem here, what is it about the rectangle again that we're trying to get? You can always, yeah, the area. You pretty much go to the last sentence when it says like how fast is the area, or another way to say it would be like what is the rate of change of the area. So we're looking at the area of the rectangle. So the formula for that is just base times height. So since we're working off the point xy, your base is x and your height is y. So your area is xy. The givens, that was everything that was given to you in this problem. So it's typically all of the relevant values or anything like that. So the first thing that they gave you was the actual function. The points, those aren't going to matter too much because that's just telling you it starts up here and stops there. But the other values that they gave you were the speed of the x coordinate. So when it talks about that, like the speed or the rate of change of the x coordinate or how fast it's changing, how do you denote that?
for the x coordinate,
Yeah,
dx over dt.
yes. So dx dt is a half. And then they gave you one other value, and that was right at the end. And that was your x equals 3. Okay, so that's all the relevant data that we need. And that's what we were given. So then the find, you're finding the rate of change of the area or how fast the area changes. So we're looking for this. So if we need the dAdt, that's what we're trying to find. How do you get it to show up? Because it's not anywhere else in here.
We'll derive the area. We'll do the derivative of the area. There we go.
Yeah. Yeah, the derivative of the area, that's how you would get the dAdt. But before we do that, we need to get the area in terms of one variable. So you either need to get it in terms of y or all in terms of x. And it usually doesn't matter which one it is. One of them is usually easier just because of what you're given. So based on what you're given here, you've got a lot of data with the x's. So let's get your area in terms of x. So we're going to substitute out the y. And unfortunately, you already know what y equals. It's just 36 minus x squared. And since it's easy, we can go ahead and multiply it out. That way you don't have to use the product rule. And you can just go right to your derivative. So 36 minus 3x squared. And we're missing something. Because with these oh, go ahead.
Dx dt.
Yeah, because with these problems, anytime you took the derivative of a variable, you had to multiply by that d variable dt, so dx dt. So it should be 36 dx dt minus 3x squared dx dt. But the other thing you could have done too is, since everything's in terms of x, instead of having to write the dx dt several times, you could just get your derivative, 36 minus 3x squared, and multiply that whole thing by a dx dt. Because essentially you're just taking the dx dt and you're just kind of factoring it out. So you can go from this equation, the area, go straight to a derivative and multiply the whole quantity by a dx dt. And that's only because every term had an x in it. So let's say it was just 36 minus x to the third. Actually, it kind of works with that one too, because that one just is a 0. But if not every term typically has that variable, you're not multiplying the whole quantity by the dx dt. Does that make sense? Okay, so I'm going to assume that's a yes. All right, so now that we have all of this stuff, what do we do now?
Well, we know what the dx dt is, so we can plug that in.
Yep. And we also know something else.
X.
the X. So yeah, stick in your X, stick in the dxdt. So X was 3. dxdt was a half. And then just start working it out. So 3 squared is
9.
9. 9 times -3.
Be negative 27.
36 minus 27.
9.
9 times a half.
9/2.
9/2. And we have units in the problem, so we can give units as an answer. So you know the x coordinate was at meters per second. So that means your area should be
Meters per second squared.
close. I think you have the square on the wrong unit.
Meters squared per second.
Meters squared per second. So area, regardless as to what shape it is or units, area is always the unit squared over seconds. Volume would be units cubed over the time, and then just a length or a distance would just be the single unit with no exponent over the time. All right, any questions on this one?
I have one. So it's a equals 36x. Is that minus x to the cubed? X cubed.
Yeah. Yeah, we just took this here and just distributed it.
Got it.
Yeah. Okay, any other questions on that one? Okay. Just for argument's sake, could this value come out as a negative? Like, would that be possible? Or does it always have to be positive?
Could it come out negative if the area was getting smaller?
Mm-hmm. Yeah, it could. So sometimes, like, it doesn't always have to be a positive answer. It can come out as a negative. So like if we would have used like x equals 4, we would have plugged that in here. We have 36 minus 48, which would have made it a negative value, which is okay. It just means that the area at that point would be getting smaller and smaller. So at some point in here, like the area gets larger and larger, but then it reaches a maximum, and then it starts to get smaller and smaller as it gets shorter and shorter and shorter. Because eventually when it hits this point, there's no longer going to be any area. It's just going to be a straight, flat, horizontal line. So there's no area to it. So the area basically starts out as a vertical line, which is 0. It increases and then it decreases until it hits 0 again. So it just kind of depends on the situation and your values, and it can come out as a positive or a negative. All right. Okay. So we spent quite a bit of time on just derivatives and their concepts. Do you want to do a little bit with integration? So the stuff in the last chapter, chapter 5.
Yes.
Okay. Let's talk about this one. Let's take the integral of 2x all over x squared minus 9 dx. It's like going crazy. All right. Okay. Any guesses as to what this is or what this integrates into?
It's a little blurry. I can't see it.
Oh, dang it. I don't know why it's. So it's 2x on top over x squared minus 9.
Is this an ln
Yeah.
solution?
Mm-hmm.
So would it just be the ln of 2x?
Not quite.
ln of x squared minus 9.
That's closer, but
With
still
the
off.
absolute value?
Absolute value. X squared minus 9 and then plus c. So when you have the integrals of a fraction like this, that is the first thing I always check. Is the derivative of the denominator on top? Because if it is, then it's automatically an ln and you're done. If it's not, then you either need to kind of tweak it a little bit or it's fitting some other format. Okay, so this one is your ln. What about 2x over x squared plus 9? So same function, we just made it a plus instead of a minus.
Should be the same, but without the absolute value.
Yeah, this one we can get rid of the absolute value bars. So why are we required to put them in for this one, but not necessarily for that one?
Because you can get a negative value in the first one and you can't in the second one.
Yeah, if you notice that the expression here is always positive, inside ln, you can eliminate the absolute value bars. You can put them in there if you want to, but you can also delete them. So that happened on quiz 12, I think. There's one of the true and false questions, I think, in the beginning.
Yeah, there was like 4 of them. I was like, oh no, I'm gonna fail this. Are these? But yeah, I was hoping you were trying to throw us up there.
Yeah, for those true and false ones, it has to be, it has to match up. So I think somebody or a couple of people were asking about, there's no plus, there's no plus C. Is that a trick question? And I was like, well, I can't really tell you until it's over. But yes, it is. Because when you have an indefinite integral, every time you integrate, there is going to be a plus C in there, no matter what. So if it's not there, that automatically makes it false. But for the LNs, you know, if it's a positive expression in there, you can delete the absolute value bars. So you can have this one. If you left them in there, that's okay too. Like I wouldn't mark it wrong. So you could have this answer or this one, they would both be true. But for this one up here, it is absolutely necessary to have those bars in there. If you say, you know, just ln of x squared minus 9, let's see, if you just said that one, that's an automatic false. Like you can't do that because this could be a negative in there, like if x was 0. That's all the absolute value bars are trying to do. They're trying to guarantee that no matter what x is, the inside is always going to be a positive. Okay, so let's try another one that's similar to it. Let's take off the x on top. So the derivative of the denominator, like it's close to the top, and now you're missing the x, you're missing the variable. If you're missing the variable from something, chances are it's not the formula you're trying to make it work. So for the LNs, you need to be off by a number, not a letter. So this one here is not an LN. You still have a fraction though. So like what, like once you check the LNs, what else could you kind of check to see if it fits?
The inverse trig.
The inverse trig. And there's no square root involved. So that means it would have to, like, which one would you have to check?
The arctan.
Arctangent. So the u squared, that's x squared. So that means u is what?
Just x.
Just x. So the u prime, you want it to be just a 1. And right now it's a 2. So you have a couple of options to deal with it. And probably the easiest one is just to take the 2 and pull it out. Okay, and then your a squared is the constant that's in there. So that's the 9. So your a is 3. And it doesn't have to square root all nice and neat. The a can be a radical if it wants to. All right, so now you just have to follow the formula for the arctangent. So the arctangent is the 1 over a u over a and plus c. So in our case, the a was 3, so that's going to be a 2/3 multiplied by the 2. U over a would be x over 3. And then plus c. Okay, let's take something similar again. Let's do 2 over root 9 minus x squared dx.
Would that just be 2 arc sine x over 3?
Yeah, so this one, he's exactly right. It's fitting the arc sine. You've got that radical in the denominator, so the derivative is clearly not on top, so it's not an ln like it was for the first two. So for your next one, the inverse trig functions, he's right. It's the inverse sine. And you can basically do the same type of thing. You know, identify the u squared. And then identify the u. So you can get the u prime. So in this case, it's coming out the same as it did before. So you can pull the 2 out again. You don't have to do that if you don't want to. Like some of you are just good at it enough already where you can just boom, get your answer. So there's no 1 over a in front for the inverse sine. But it still is the u over a. So x over 3. Let's see. Okay, let's take one more variation on those. So we'll stick the x back in there. So the 2x is back on top, and then it's over the root 9 minus x squared. So it's no longer going to be an inverse sine because it's not fitting that format, because now you have a variable up there. It's not fitting the ln either because you need the derivative of the entire denominator, not just the stuff inside the radical. So if it's not an ln, if it's not an inverse trig function, what other kind of thing could it be? Or what other method could you try to use? It's a what?
Can you, I don't think you can use ln, but can you actually take out the square root or?
Oh, so make this like 3 minus x, like root the
Maybe.
9 and root that. You can't. It would be really nice if you could, but that does not follow order of operations, so you're not allowed to do it. Is that what you meant?
Yeah,
Okay. Yeah, that's not an option. You are kind of close to it though. In the phrase where you said take out the 9 minus x squared, you can do just that. So this is going to be a u sub. So if it's not ln, if it's not an inverse trig, then you can try a u sub with it, and that's probably what it is. So in this case, our u is going to be everything that's inside the square root. I think it was a quiz. Might have been the exam too. I can't remember which one it was. I saw there was a problem in there, and I saw a lot of people saying u is equal to x or something. That's the u sub they wanted to use. If that's what you're choosing for u, stop, because you're not doing anything. You're just changing all the x's into u's, and you haven't done anything. So u has got to be some quantity or some expression involving x more than just x itself. Okay, so then the du is negative 2x dx. So you're close to that. You need a negative 2x. So put a minus inside and outside. So now you really have negative integral 1 over root u du. So to deal with this, flip it up to the top and make your exponent negative. So u to the negative half. And then integrate it. So add 1 to your exponent. So negative 1/2 plus 1 is a half. And then you're going to multiply by the reciprocal of your exponent. Should just be 2. And then plus c. And then after you integrate it, then just get everything back in terms of x. And you're done. You don't have to change the 1/2 exponent back into a square root. You can leave it as a 1/2 power. That's also an option. Okay, so 5 integrals that are really similar, but they have different ways to do them. If one little thing is different. So when you're looking at your integral and you're going, okay, well, which one is this? You know, is this an ln or is this whatever? You know, you run through just a little checklist. You know, you can see if it fits ln, and see if it's inverse trig. And if it's not either of those, then you can see if it's a u sub. Because if it's not something that you can just look at and integrate, it's going to be one of these 3. So if there's a fraction, check the ln first. If it's not that, move to your inverse trig. If it's not that, then move to the u sub. All right, so we've got about an hour left. So what other stuff do you guys want to do? Like what would be like your individual questions and stuff? Like, do you have any questions on a study guide, a previous exam? What do you want to know?
I have a question. I don't know if you already covered this because I just recently joined, but on the test, are we going to have to remember some of the older methods for finding derivatives, like on chapters 2 and 3? Kind of like I don't remember the exact method, but it's like you have to do like a fraction thing.
Oh, the limit definition.
Yeah, like the
So
f
like the
x minus h.
no, I'm not going to ask you one on that. I mean, I can stick one in there real fast if you want one.
No, we're good. No,
No thanks.
Okay,
derivatives are perfectly fine.
sure.
But I have a question.
Yeah,
So it's from, is it, can I ask from one of the quizzes?
sure.
It was from the first quiz. It was like use the graph to find each value, and then if the value does not exist, type DNE. So it was like the find where the limits are on the graph.
Okay, do you want me to do the same one or just make up another one?
You can make up another one. That'd be great. Either one works.
Okay. So let me pull up that quiz just to make sure I'm answering something that you're looking for.
The first quiz. For the
Okay.
semester.
Who's talking?
Oh, Sid.
Okay. Okay. All right, that's a lot better. Okay, so you have the parabola. Whole. Okay, so that's 4. And that this x value is -1. This one is -3. Okay, so the first one, the limit as x approaches -3 of the function. So the point wasn't drawn there. I just did it just to do it, but it doesn't matter. Some people, I think they answered it and they were like, "Oh, it's DNE because there's no there was no physical dot." But as long as there's no open circle or vertical asymptote, then it's the function exists there. Like I know there's a point here, there's a point here, there's a point there, there's a point there, because there's no open circle. So whether there's a dot on it or just solid graph, it's the same thing. So you're tracing from both sides of -3 from the left until you get to -3, and then you're tracing on the right until you get to -3. And they both look like they're going to run into y equals
0.
0. And some people, they were getting stuck too. They were like, well, I'm tracing over, but then I can't get over there because there's this hole there. And it's like, yes, you can, just jump. Like, don't stop tracing until you get to this x value, even if you have to jump over something across. Like you don't stop until you get there.
Yeah, because that's why I get confused. That's why I get confused at too.
Yeah, like if you can look at it this way too, like if I was going to actually draw this function, if I had the function, not the graph, and it said, hey, graph this, like you wouldn't just go an open circle and go, oh, well, can't do anything else. Like, no, you would just draw the rest of it, right? So if you could draw all this, then you can definitely get back to it. So don't let a hole or an asymptote stop you. Just jump over it. Okay, then the next one, x approaches -1. So this one tracing from, oh, it is, yeah, just -1. So tracing from the left, that's hitting at y equals 0. Tracing from the right, that's hitting at y equals -1. They're different values. They're split. They're not connected. So that is DNE. Does not exist. Okay, then C, the limit from just, whereas x approaches 1. It's kind of the same thing. You trace over till you get to 1 from the left, trace over till you get to 1 from the right. They're split again. From the left is -1, the right is -2. They're different values. So it's a DNE. And then D, the function value when x is 1. So now you're looking for where the point actually exists. And so when x is 1, the point's up here. So the y value of that point is 2. So the answer is 2.
And then so for B it's D&E because it's open.
No, because they don't match.
Oh yeah, because let's see here. Oh yeah, they don't match.
Yeah.
Is a jump between those two dots.
Yeah, because the left value is different from the right value, so that's why it's a DNE.
Got it. So if that line was diagonal, it would have worked.
It was diagonal.
The bottom one is so if the bottom the closed dot was up there, it would have worked.
Yeah, if it would have been like here,
Yeah.
like the green one, yeah, now the limit would be 0 because now they're meeting, or they would, it looks like they would meet at y equals 0.
Got it. Yeah, that helps. Thank you.
Sure. That helped me too. I meant to do one of those and I forgot. All right, what else?
Can we look at the, I don't know if it matters, or I was just kind of curious about the exam 3, that acceleration or the velocity one that was thrown out. Question 21.
Sure. Let me get to that one. Exam 3.
Yeah.
Exam 3, number 21.
Yeah.
Oh, this one, yeah, this one I tossed it out. Mainly because I I knew what I wanted, but I knew what I wanted to do. It just, the function I threw in there did not accomplish what I was thinking. What I should have done with it is given you an interval to search in, because technically, if the particle was going along that curve, there would be no maximum or minimum velocity. Like it would just keep increasing and increasing and increasing because it's a polynomial. So that's why I tossed it. So a lot of you did what you were supposed to do, like you found, like you got the derivative of that function, so that gave you velocity, but I wanted the maximum of velocity, so you now have to take the derivative of the velocity and then go from there.
Okay. All right, then yeah, okay. So I think I got it. That's kind of what I was thinking. I was looking over something on the study guide. I think I saw something similar. I'm like, oh, this one has an interval. Okay, this makes sense. Okay, yeah.
Yeah. Yeah. Yeah, anytime you want the maximum or minimum of something, you got to work off the derivative of that something. So if you want the max velocity, you need to use the derivative of velocity.
Yeah, and that came out with, I think it was time equals 3 or 4. And then I
Yeah.
used 3, but then I was looking over it again. I'm like, oh wait, 4 is way bigger. So I guess it would have just continued going up then, no matter what.
Yeah, it just increased with no bound, and I was like, dang it. So yeah, the one on the study guide is a lot better. So do you want to do the one on the study guide?
I'm okay with those. I was just,
Okay.
yeah, curious what the answer was on that one. But yeah, that makes sense.
There wasn't one. It's like I toyed with making it just as a bonus problem, but there was just a lot of varieties of answers that I was getting. So I was like, I'm just going to toss it and just do what it did. All right. Let's see. What else do you want to do?
I have a quick question for
Mhm.
for question 12 on exam 4. Can you work through that one? Because I didn't get the answer for that. And then when I went back and I tried to do it on my own, I still didn't get it.
Okay. Yeah, let me pull yours up.
I can read the question if you need to. It's involves the trapezoidal rule.
Let's see, I'm almost there. Oh, I think I know which one you're talking about. Use the trapezoidal rule to approximate the value with n equals 4, that one?
Yeah, that one.
Okay. All right, so we have integral from 0 to 4. 1/1 plus x dx, but we're using the trapezoidal rule. This one, you could actually evaluate this one. If I just said, what's the exact area? You could actually integrate this and just plug in the bounds. So that was one of the solutions there. I think that was the ln of 5. But it wanted you to approximate it. Where n is 4. Okay, so basically you have 4 trapezoids that you're going through. So you can either, use the actual rule that was there, or you can just get the area of each trapezoid and add them all up. And it should come out to the same thing. So do you know what you were doing?
So the area of the trapezoid is 1/2 times height times base 1 plus base 2.
Yeah.
And then I used the trapezoidal rule where it's f of a plus 2 f of, I think, x1, where you just multiply by 2 until you get to f of b, and then you add
Sure.
it up.
Yeah. Okay. Yeah, you can do either one. So since you said the area first, let's just do that one. So the height of each one of those trapezoids is going to be 1, because you're going from 0 to 4 with 4 intervals. So if they're all evenly spaced, that means each interval is a width of 1. So your trapezoids. Okay, so your curve is doing something like that. Your trapezoids are running up and down. So they're like this. So the height is actually going horizontal, which is weird. And the bases are the ones that are going up and down. So for your first trapezoid, when you say like base 1 plus base 2, so your first base is be when x is 0. So you plug that into your function. So that'd be 1. When x is 1, you get a half. So your second trapezoid, x is 1 again, so it's that half. Plus when x is 2, you get a third. Next trapezoid when x is 2, so a third. And then the next one was when x is 3. So a fourth. And then the last one, so didn't draw, is when x is 3. Plus when x is 4.
Okay, actually, I think I know what I did wrong. I must have just done my math wrong and like multiplied it wrong or something. Because I don't know why I kept getting like 101 over 60 or something. I don't know. But I see what I did wrong. But
Yeah, that's what I got too. I remember
That's what
that.
I got.
Yeah. I didn't try it by adding up the areas though. I was doing that that equation.
The
Yeah,
b minus a over 2n. That one,
Which one?
the b minus a over 2n times that big old quantity.
Just the f of a plus 2f of x1, x2, x3, f of b.
Okay. Yeah, that's basically the same thing. Because your b, let's see. Because if you look at all these, like the 1/2 and the 1, that's in every single quantity. So if you pulled it out, here's your f of 0. Oops. And then you have 2 f of 1s, right? You have 2 1/3, 2 1/4. And then you have the single 1/5. So that's your f of 0 to f of 1 to f of 2 to f of 3, and then f of 4. Okay, so 1, 2. Common denominator is
is it 30?
Yeah. So this is looking like it should have been something over 60. So I don't know why that's not a choice. Lewis, what did you do? All right. Let's see what it actually should be. Okay, so multiply that by 10, 15, and 6. Okay, so if you add all the numerators up, uh, 21 and 20, 41. Add it to 2, 101 over 30. Is this what you said before? 101 over 60?
Yeah, because
Yeah.
I had gotten it wrong before, and then I went back to check, and then I still got that.
Okay, I'll have to go back and look at that and see why that was not a choice. So I'll investigate that later on today. Okay, so that was, which is exam 4. Number 12. Okay. I can't remember if this was, we've had 2 options for this. So I might have pulled in the answers from the other problem, but I'll look at it. So you might see your score go up.
All right, thank you. That was my last question.
Okay. All right. Let's see. What else do you guys have?
Actually, I have one topic.
Sure.
It was I think you gave us like 3 options to say which one of these is like would Rolle's theorem or the mean value theorem would work for. It was one of those let me see if I can find the exact like topic. I think it was, what chapter was it on?
That would be
Section 4.
chapter 4,
Chapter 4, yeah.
section 4.2, I think.
Yeah, I think is there a question like this on the there's a quiz question. I'm trying to look for it right as we speak. So was a quiz 5? Here's it's quiz 6.
Quiz 6.
Yeah. Is which of the following would Rolle's theorem apply?
Okay, what was your first option?
It was f of x equals f to the 4 divided by 4 divided by 3
4/3.
and 4/3 on the interval of -1 to 1.
Okay, so Rolle's was to which? Okay, so x to the 4/3.
With the interval of
and
-1.
1. And g of x equals secant.
Yep.
Just x. And 5 pi over 6 is 7 pi over 6. And then 3. Polynomial x to the 3rd minus 13x plus 12. Oops. -2 to 1. Okay, so which of the following, or yeah, which of the following can you apply Rolle's theorem? So Rolle's theorem, there are 3 things to check before you can say, oh yeah, it applies, or no, it doesn't apply. So what are the three criteria?
It must be continuous.
Mhm.
Does it have to? Does it have to fit within an interval?
Continuous on the interval.
Has to be differentiable.
Yep.
On A to B.
And then what's the third option?
F of A has to equal F of B.
Yeah. Okay, so if you can apply all, or if all three of these conditions work for your given function, then you can apply Rolle's theorem to it. So for f of x equals x to the 4/3, first off, is it continuous on this interval?
Yes.
Yeah, you can plug any number you want from -1 to 1, and you can get an answer there. Okay, second one, is this function differentiable from A to B? And another way to ask that question is the derivative continuous. And if you're not sure just by looking at the given function, you're like, well, I don't know if the derivative is continuous or not, then get the derivative. So your derivative would be 4/3 x to the 1/3. And that is continuous itself on that interval -1 to 1. There's no value that you're not allowed to stick in there. So it's continuous, it's differentiable, and then just check f of A equals f of B. So if you plugged in -1 and 1, you get the exact same value. So all three of these conditions hold, so that one works. So you can move on to the second one. So for secant, is it continuous on this interval?
Yes.
Yeah. Secant has those vertical asymptotes, but they're at the pi/2s. So pi/2, 3 pi/2, 5 pi/2, and none of those are in this interval here. So it's continuous. Its derivative is just secant tangent. And the derivative is continuous as well. You can plug in any number in there into the derivative and it's fine. So then you can check f of A equals f of B. So secant of 5 pi/6 and secant of 7 pi/6, those are both equal. They both come out as -√3/2. Okay, so then the third one, it's a polynomial. So it's guaranteed to be continuous on any interval. So that first one's good. The derivative, 3x² minus 13, that's still a polynomial. So it's also continuous. So it's differentiable. And then the last one, f of A equals f of B, is h of -2 equal to h of 1. So you just got to plug it in and see if it is or not. So if you plugged in -2, that would be -8 plus 26 plus 12. And then if you plugged in the 1, you have 1 minus 13 plus 12. So h of 1 is 0. H of -2, if you add these up, is not. Because that would be 30. So just the first two. So what would change if instead of saying Rolle's theorem, if we said the mean value theorem?
F of A wouldn't have to equal F of B.
Yeah, so that third criteria would just be gone. So you're just checking the first two. So if we would have said the mean value theorem, then all three of them would work. All right, let's see. Keep going.
Let's see, when would a cubic have more than one horizontal tangent line, or more than two, I mean?
When would a cubic have more than two?
Yeah,
It can't.
okay, maybe I misread the question. Let me see.
It's like, yeah, there was either a quiz or I want to say it was an exam question. Was that I think it might have been the second one. And of course, now Canvas wants to be slow.
Okay,
There it goes.
so the graph of every cubic polynomial has two horizontal tangent lines.
Oh, okay. So a lot of them do.
Oh, but it could have less than one. I
Yeah.
mean, less than two. Okay.
Yeah. Because a lot of the cubics, they look like that N shape, but X to the third just has that one single slide in there. So that's where you have your horizontal tangent. So there's only one. So the N-shaped graphs have two of them. But if it's just a quantity to the third power, then there's only the one.
Yeah, I don't know. Yeah, I don't know where my head was at. I was like, how can I have more than two? I don't understand.
Oh.
Right.
Which number was that?
17.
17. Okay, yeah. Or yeah, okay. Okay, any other questions? It's like I thought of one, but I'm pulling it up just to make sure, but you can ask anything else. Actually, let's talk about exam 3. Yeah, exam 3, number 1. There were a couple of varieties of that question, but they were talking about the concavity. So one version was, where is y equals 1 over x squared concave down? Basically. So you have 2 options for this problem. One of them is to, start taking the derivatives, start going through that number line thing and see where it's concave up, concave down, all that stuff. But the other option, which might be a little faster, is to just use the graph. So like 1 over x squared, if you know what it looks like, will speed up the process a lot faster than going through all the derivatives. So like 1 over x squared, anybody know what it looks like?
Goes up. So from the left all the way to infinity, and then from infinity to the other way, the opposite.
Yeah. So it's a lot like 1 over x, but that bottom part's been flipped up, more or less. So this is the graph. So if it's asking where is it concave down, looking at the graph, where is it concave down?
It's not.
Yeah, it's not. So just nowhere. So if the function, if the given function is pretty simple, just graph it and see if you can visually see what it's asking for. So like the other one, it was the same question, but it was, the function was negative 1 over x squared. So it's basically this graph just upside down. So where is this thing concave down? Negative infinity to 0. And then 0 to infinity. So sometimes you can get away with, just graphing the function, and then it'll tell you. It was kind of the same for question 6. Like you had 3 functions given to you, and then it asked like where the function increased, or some options where it decreased on a given interval. Instead of having to run through all the derivatives, you can just look at the graph and see what they were, and if it matched up to the interval in question.
Yeah, that's a good idea. I didn't even think of that now looking back at it.
It's like people who know their graphs can shortcut some good stuff like that. So if you're really sharp with like your parent functions and stuff, it can make things go a lot faster. So like for example, which increases on the interval 0 to infinity. You had 3 options. F was x squared plus 2. G was sine of x. And H was 1 over x. So x squared plus 2 that's just a parabola with the vertex right there. So it's going up from 0 to infinity. Sine of x, that's your wave. So that went up, but then it went down, then back to up, and then down. So that's a no. And then 1 over x, that's the graph, but you want it to increase from 0 to infinity, and it decreases. So that's another no. So it's just that.
Can we go over number 5 on that same exam, on exam 3?
Sure. Did you have a point of -3.8 or a point of -4, -7?
I had -3.8.
-3 and 8. Okay, so a polynomial has a relative maximum at -3 and 8, so up there. A relative min at 1, -5. And another relative maximum at 4, 6. This is clearly not to scale, but we don't care. So how many x-intercepts does it have? Okay, so we know this is a relative max. This is a relative min. And this is a relative max. So if you were told that it was a polynomial, so you just have to fill in the rest of it. So 1, 2, 3, 4.
Okay, that was a lot easier. I have no idea what I did on that. Got that one.
If you didn't know it was a polynomial, you wouldn't be able to do that
Okay, yeah.
because you wouldn't know how the end behavior was, what that was going to do. The other version, I think it was pretty much the same way it was, but I think that graph went this way, more or less. So I think, pretty sure it did. So it was just upside down, but it still had 4 intercepts. All right, let's talk about, it's the same exam, but this one was question number 2. You were given a function and determined the x coordinates of the inflection points. And there were 3 options, but all of them did pretty much the same thing. So I'll do the first one. So f is equal to x to the 5th plus 5x to the 4th plus 84. So inflection points, you need the second derivative. So the first derivative, 5x to the 4th plus 20x to the 3rd. Second derivative, 20x to the 3rd plus 60 x squared, and then you set it equal to 0 and solve for x. So you can pull off a 20x squared, and you're left with x plus 3. So your solutions for that equation would be 0 and -3. And that is where I think at least half of everybody stopped. And they saw that this was one of the solutions, or one of the choices. You can do that with a critical number, but you cannot do that with inflection points. Because inflection points, there has to be a change in concavity for it to be an inflection point. You don't know that yet. You just know where there's some possible inflection points. So you have to test them. Whether you want to or not, you have to test those second, what makes the second derivative 0 or undefined. And see if there's a change in concavity or not. So for the -4, it comes out as a negative, the -1 comes out as a positive, and the 1 comes out as a positive as well. So there's no sign change at the x = 0, but there is at just the -3. So be careful when it just wants to know where inflection points are, because you might have an answer that really isn't an answer. Let's see, let me do number 15 really quick. Or two versions of this one, but they are both done the same way. So it gave you a curve in a single point, and it wanted you to order three different values. So the function value, the derivative value, whoops, and the second derivative value. Got ahead of myself. And it wanted to know which one was the biggest, which one was in the middle, and which one was the smallest. So there's only, out of the three, there's only one value that you know for certain. And that's the function value. Because it equals 0, because it hits the x or the x-axis. So the function value is 0. You don't know the exact values of these two, but you can tell if they're positive or negative. So this curve right here, is this concave up or concave down?
Up.
Concave up. So if it's concave up, is the second derivative positive or negative?
Positive.
It's positive. And then this curve, is it increasing or decreasing?
Be decreasing, so it'd be negative.
Yeah. So yeah, so the value of the derivative is negative there. You could also, if you wanted for that one, think about what a derivative is. What is a derivative?
Slope of a tangent line.
So the tangent line. So if you drew in a tangent line there, does it have a positive or negative slope? Negative one. So the derivative is negative, so that's the smallest one of the two, or the three. The function is 0, so it's in the middle, and then the second derivative would be the biggest because it's positive. So the other version, the graph was upside down, so it flipped the order.
Real quick, just not about this, but next semester, do you know if everybody uses the same book or if FLC does?
At Folsom, we do. I don't know about the other colleges.
Okay, cool.
And you should also, well, at least it was a year ago, they were also giving you an option between the 4th edition and the 6th. I would think that would still be true, but I don't know. We haven't talked about that as a department for a while. If you have the 6th edition, you should be fine.
Okay. Yeah, I picked a class at FLC just so hoping that they would use the same book.
Yeah, I'm pretty sure they do. You could always contact them and ask them.
Okay.
Or it might say in the schedule. And in case you're wondering too, both professors, Professor Fusen and Professor Clayton, are really good.
Awesome. Yeah, I was gonna ask. So yeah, that's good to know.
Yeah, I do not think you would be disappointed. I think Clayton, I think his classes are in person or on ground. And Fusen, I don't think she's on ground, but I think it's still online, but it's a set time. If I remember right. And
Yeah.
what times they are, I have no idea. But they're both pretty good. You definitely have to stay on top of it though. Calculus 2 is in my opinion, out of the 3, probably the toughest.
Oh, is that why you said it was the most fun?
It could have been. I don't know. I just really like it. Calc 3 is, I think, the easiest. And Calc 1 is in the middle. But so Calc 2, you definitely have to stay on top of stuff. So if you found yourself getting behind in this one, you don't want to do that next semester. Because it's fast. And it moves along at a pretty good pace. And there's just, the problems just get longer too. There's a lot more algebra because you start with more integration techniques and then you start moving into some other stuff. So yeah. You can, I mean, you'll always be able to go to your current professor, but if you ever have questions, you can still ask me for help because I like all that stuff too.
Okay, I'll hold you to it.
Which just revealed how much of a math nerd I am, but there you go. I'm also the teacher, so go figure. So I'm trying to think of what else I could tell you about the final. It's pretty comprehensive. Like there's limits, there's derivatives. The format's kind of the same. So there's multiple choice. There's fill in the blank. There's true and false. And free response. There's a total of 34 questions. But if you know what you're doing, it shouldn't take you the whole 3 hours to do it. Let's see. What else do you guys want to know? What are the questions you have that I didn't think of?
I have a question about like the grading of it. So, like when someone says like it's 25% of your overall grade, like if like obviously I'm not gonna get a 0 on it, but like if you get like a certain percent, does it like subtract the percentage you didn't get from your grade like by a quarter, or does it like average out? I don't know how to explain.
um, yeah, I think a good rule of thumb is like if you know what grade you have right now. So let's say you had a 70 in the class. If you get a 70 on the final, then your grade should pretty much stay the same, I think, because it would match. Is that kind of what you're asking?
Yeah, I guess. And
Yeah.
like if you get like, for instance, like if I did have a 70 in the class and I got like 50 on the final, like I obviously I hope I don't get 50, but like
You too.
your grade wouldn't go any further down, like it wouldn't go any further below 50%. Like
No, but if you have a 70 and you get a 50 on the final, that would
I
drop
would still,
into the
yeah,
teens.
that would fail me.
But it
So
would
like I was just trying to, it's just an example, but
okay.
yeah.
If you had a 70, well, let's say you had a 75 and you got a 65 on the final, that would definitely drop your grade. But I don't think it would drop it enough to make it a D.
Yeah.
But it would be close.
Okay. I don't intend on doing that. It's just like, I don't know, I have this thing
Good.
before any test. I'm always like, okay, what's the worst possible thing that could happen?
Oh, sure. I know somewhere in there Canvas has a what if scenario, so you can kind of play around with it yourself. You can also use, if you want to do it the long way, yeah. So you can take, so it'd be like 0.55 of your exams percentage. Because I think, I mean, it breaks it down for me. So I'm assuming it breaks it down for you guys too. It like shows your exam percentage. It shows your quiz percentage. And then plus the final. So what you can do is you can stick in your exam percentage, stick in your quiz percentage, and then set this equal to whatever you want in the class. So say you want a B, set it equal to 80, and then just solve for that. That makes sense. So like if your exam percentage was say, an 85, and your quizzes were a 90, you can let your final exam score be X. If you want to be in the class, just work it out in the solve for X and it'll tell you what you need to get on the final to get that grade. If it comes out as a negative, that means that you can't get the score. You would have to get something higher. And if it comes out as over 100, that means you probably can't get that score because now you have to get more than 100 on the final. That makes sense.
So as
it'll
long
be,
as it's not negative.
well, negative would be good
Yeah.
because that means you're getting higher than whatever this is.
Oh, okay.
Over 100 is the one that says, yeah, that scope, that grade is not possible. So for some people, you know, if they got a 0 on the final, would be impossible for them to get an 80 because these two scores are that high.
And I did find the thing where you can like plug in a random score to see how it affects your grade.
Okay,
That's
okay,
really
cool.
cool.
That's the fastest. So there you go.
I had a question about the 2% rounding.
Sure.
So does that apply? So does it have to be within 2% before the final or after the final? So say like I get a 78 after the final, and then I ended up getting an 80 on the final.
After the final. So once everything's all like all your scores are stuck in. And so you have a final, so you have an overall grade with everything. So and it comes out to a 78%. So this is with the final exam stuck in there. As long as you have an 80, on that final exam, then that would round this to an 80 as well. Does that make sense?
Yeah, that makes sense.
Okay.
It just so the final does get counted.
Yeah. Mhm.
And then if we did the math 80 class, I forgot, did you say you were adding 5%?
Yeah, to your final exam.
Okay, cool.
So if you got 100 on the final, and you took that course or the LTAT 30 or 31,
Mhm.
then it is possible for you to get 105. So I got the list from Professor Olson. So I know who took the Math 80 class, and then I'll get a list from, I think, Professor Armbrust, and she'll tell me who took the learning skills courses. So I should get that one pretty soon as well. So
Right.
those points would be listed somewhere in there. It says like fudge points.
Mhm.
That's where I would throw it in. So if you took one of those two classes, you should have at least 5 points in there. If it's more than that, that means I curved it and gave everybody so many more points.
All right, well, thank you.
You're welcome.
Yeah. This has been a fun class,
Oh, good.
but it's
Yeah.
been a challenge.
Mhm. I totally get it. I wish it was face to face as well.
Yeah.
But yeah, it is what it is. But yeah, I had fun too. It's been a good semester.
Well, I appreciate the format of everything too for an online class.
Oh, good. That's nice to hear.
Yeah, I took you for 370 last semester or over summer. So yeah, it's been good.
Okay. Oh, so you've already met Professor Fusen?
No,
Oh.
well, I took you. Actually, I know her in real life, but
Yeah. Well, that's when, or don't you, like, her daughter was.
oh, okay, yeah. I teach her daughter riding lessons.
Yeah.
I ride and train horses. Yeah.
Okay. Cool.
Yeah.
All right. Well, if you guys have any other questions, just let me know.
All right. Thank you.
You're welcome. And yeah, I'm gonna try to have the finals graded hopefully by Tuesday, Wednesday of next week. And that should be it. All right.
Awesome. Yeah,
Okay.
thank you. Yeah,
You're welcome.
Christina said, it's been a good class. Appreciate it.
You're welcome. All right, we'll talk to you guys later.
All right, bye.
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 Oh, I'm trying to get her to stop.
Just answer.